In this video, we want to look at how to visualize systems of equations. All right, we're going to use the equations that we had seen in class. All right, so these have been entered in matrix form, which you're about to learn about or review. So if you look at the top row, this is the matrix form. It's an augmented matrix where we had 1, -2, -1, 1. That represents the equation 1x, or just x, minus 2y minus z equals 1, right? The second row is second equation we had in the class example. There were no x's, okay? But in matrix form, you have to enter a 0 there. And then you have 1y plus 2z equals the constant 5. So the c on the top represents the constant value of 5. And then in the last one, we're simply looking at the equation z, because there's 1z equals 3. Right? So we had this system of equations, and we were able to use sort of back substitution from the third equation into the second, and then the combination of those results into the first to determine that the answer was, in fact, that x was 2, y was -1, and z was 3, which is the intersection point of the planes. Okay? Now I want to go over some of the details. All right, so let me hide my picture here. As we look at this image here, okay, over on the right, okay, the x, y, and z planes follow the red, green, blue pattern. If you work with LEDs on TV screens, they're red, green, and blue, and we can make all of the colors out of them. And it's always in that order: red, green, blue. So x is represented by red, the y-axis is represented by green, and the z-axis is represented by the blue axis, right? Now let's consider the bottom equation, the z equals 3 equation. So once again, we're following the order red, green, blue for the planes that we're producing. So the last row produces the blue plane. Okay, what can we see about that? Well, that's a nice plane that looks flat. By flat, I mean it's parallel to the x, y axis. Okay, it's at the same height everywhere. It's parallel, it's the same z value everywhere, I should say, which makes it parallel to the x, y axis. All right. So it's simply z equals 3. The x and the y are missing values. Those are zeros in the matrix. And since those are zeros, we know that this plane is parallel to the x, y axis. All right. Then when we look at the second row, okay, it has a 0 in the x column. So we need to be parallel to the x-axis, but we'll have an equation in the yz plane. All right, so what does that look like? Well, that would be the green, because it goes red, green, blue. That's the green plane being represented, okay? And you can see that if we look at it kind of head on in the x direction, okay, so the red axis is pointing almost out of the page at us, we get a line that's in it's the green axis and blue axis left. That's the xz plane. We get this downward sloping line in that plane. Okay, but if you consider that it could have all x values, then you extend it forever in both the positive and negative x direction, and you get a plane that is, never touches the x-axis. It's parallel to it, but it is a line in the yz direction. Okay, then the top equation has x, y, and z in it, so it's not parallel to any of the axes, and so that gives us the red plane. Okay, so that's skewed in all of the directions. Okay, and so because it's not parallel to any of the axes, there's an x-intercept, a y-intercept. Let's see if we can see those. It's kind of hard to see where they intersect, but it intersects the x-axis and y-axis. You can see there, and then that's a pretty good angle. You can see it. It also intersects the z-axis at a negative point on the z-axis. Right now, those 3 planes, any 2 of them combine along a line. So look at the red and the green. Okay, you can see there's a line where the red and the green intersect. My little cursor is following that. Those intersect along a single line. Okay, the red and the blue intersect along a single line, which we can see pretty well. Actually, if I take the transparency way up. Okay, it's a little bit easier to see. Red and green, it's less transparent now. The red and the green intersect along a clear line. Red and blue, you can see it from the front there, are intersecting along a line. Okay, and then green and blue clearly are intersecting along a line as well. And those three lines of intersection all come together at this point. Okay, the third plane, whichever one you want to call the third plane, cuts the line produced by the other two planes at a single point. And in every case, that's the point 2, -1, 3. All right. Now in class, we had gone on to a couple of other examples. I had changed this to a -x, okay, and then it was 3y, and plus 3z was equal to 4, and then the third plane was 2x, given by 2x minus 3y plus 1z is equal to 10, and if I graph that, you can see we have all three planes have intersections with all of the axes. None of them are parallel to any one of the axes, but you can see they come together at exactly the same point as before because it was arranged to work that way. Let me take the transparency way down so you can see through them a little bit more, and you can see how they kind of align with the axes a little bit better. But they all come together at this point in space, 2, -1 in the y direction and 3 in the z direction. All right, so 2 in the x direction, -1 in the y, and 3 in the z direction. So let me up the transparency a little bit, and you can kind of see that again, how they intersect. Right. Then we took this and we made a small change to it. Okay, we kept the first two equations the same, but I made this, the third equation just became a 1 in the x direction, a -1 in the y direction, -1y, plus 1 in the z direction, and that summed to 2. Okay, now let's graph that. So it was x minus y plus z equals 2. All right, and when we look at this, it says there are no intersections of the planes. All right, it's not clear from here. We can see the line where the blue and the green meet. We can see the line where the red and the green meet, and there's a line down here. You see where the red and the blue meet. But what's interesting, if we turn it just the right way, we can see right down the middle of it all. Okay, what we have are three planes. The lines of intersection are all parallel to each other. So instead of the lines of intersection all meeting at a point, the lines of intersection are all parallel to each other. And so because of that, this system of equation has no answers, all right? It's unsolvable. There would be no solution for x, y, and z, all right? And when we looked at it carefully, we saw that if you were to double the first equation and add to the second, they would match up except for this constant. This constant was not double 1 plus 2 plus 4, okay? It's off, okay? So that led to this solution where the first three things, we took double the x, y, and z of the first row and added it to the second row to get the third row, and it created this no solution scenario, right? If, on the other hand, I doubled the first row entirely and added to the third row, including the constant, then this becomes a 6. And when we did that, we get an infinite number of solutions. Okay? You can see all of the planes meet on a single line, and there are an infinite number of points on that line. Now, this is a line in 3-dimensional space. Okay? So we need to describe it parametrically. So it's sort of arbitrary, but we choose to let z just equal t. Okay, so t will be linked to the z value, right? When we solve this system, then we could write y in terms of t, and we could also write x in terms of t. and come up with those equations, those parametric equations for x, y, and z. But the trick is first just let z equal t, and then substitute that back into the other equations in order to get these relationships. Okay, so there you have it. They all end up meeting on a line. So we have basically three possibilities. The planes can meet at a point. The planes can meet nowhere. There's no common intersection between all three. Any two will meet. That was when we did this, when we had a 2 here. No, there's no point where all three planes coincide. Okay, so we kind of get this hole up the middle, and there is no solution that makes all three true. You can never be on all three planes at the same time. You can be on 2 of the 3, but you can never be on all 3. Right? But when we throw that 6 in there, there are an infinite number of places where we can be on all 3 planes. And that's a line that must be described parametrically in 3D space.